Hey everybody, welcome back to Mr. A's geometry course. Today we're starting Unit 5, which is all about triangle measures and triangle congruency. Let's get into it. Unit 5 starts here with a lesson on the basics of triangle measure. And we're going to start with making sure that we possess good vocabulary for triangles. So we're going to start with making sure that we have the right names for triangles as we learn how to classify them. Right? So there are two attributes that we're going to use when we refer to triangles, when we name triangles. Those attributes are going to be side length and angle measures. So the length of sides is going to give us a type of triangle, and the angle measures of all three angles in the triangle will give us a name for our triangles. So again, in case you don't know, that's a triangle, three sides, three angles. When we're referring to triangles by their angles, we can classify them in three ways. We have acute, right, or obtuse. Here is the criteria for these three ways. For an acute triangle, all angles, all three of them, will be less than 90 degrees. So less than 90 is an acute angle. So if all angles are acute angles, then we call it an acute triangle. A right triangle will have one angle that is exactly 90 degrees. And an obtuse triangle will have one angle that is more than 90 degrees. So again, in an acute triangle, all the angles less than 90. A right triangle has one angle that's exactly 90. An obtuse triangle has one angle that is greater than 90 degrees. And here's a visual reference for you for each. To know a triangle is a right triangle, we need that box for a right angle. For an obtuse angle, we need an angle that opens up more than a capital L, like that angle right there being greater than 90. Notice the other two angles in the obtuse triangle are acute. So they're not all obtuse. That's impossible in a triangle, as we'll come to learn. Only one angle would be more than 90 degrees. Same kind of thing goes for the right triangle. Those other two angles have to be acute. I cannot have multiple 90-degree angles in a triangle. It's impossible. We can have, though, all three angles being acute, which would make it an acute triangle. We can also refer to triangles by their sides, and we can classify them in these three ways: scalene, isosceles, or equilateral. A scalene triangle has no congruent sides, none at all. An isosceles triangle will have two congruent sides, and an equilateral triangle will have three congruent sides. Remember, congruent means equal in measure, so we're referring to the sides being the same length. Okay, and here's an example visual reference here for all of these. So maybe a little hard to see here, but I got one dash on all three sides. Notice also all the angles are congruent to each other. That's what make this an equilateral triangle. In this figure, we have two congruent sides. That makes it an isosceles. And if none of the sides are marked, or we know they're not all the same length, we call it a scalene triangle. Maybe the most important theorem of geometry here, the triangle sum theorem, says the sum of all angles of any triangle that has ever existed or will ever exist, the sum of all three angles has to be 180 degrees. As we look at this triangle over here, we have angles A, B, and C. For absolute clarity here, what we're saying is that the measure of angle A, when added to the measure of angle B and the measure of angle C, that's all three angles, they must add up to 180 degrees. This is true, again, no matter what type of triangle it is. Scalene, isosceles, equilateral, right, obtuse, acute. All three angles in any triangle must add up to 180 degrees. That's the triangle sum theorem. We apply the triangle sum theorem by solving for missing angles or variables inside of triangles and the angles of triangles. So our first example here, we're applying the triangle sum theorem to find the missing angle, which is angle T. And again, our theorem tells me all three angles must add up to 180 degrees. So our missing angle T, measure of angle T, plus angle A, which is 27 degrees, plus angle M, which is 82 degrees, must add up to equal 180 degrees. And we have some basic algebra we can do there to solve for the measure of angle T. If we combine our 27 and our 82, that would give us 109 degrees there on the left. Then I can subtract that 109 from both sides to find the measure of angle T. 180 minus 109 would give me 71 degrees for that angle. All right, let's see if you can do these basics here on your own with this example. Go ahead and pause the video and make sure that you can find the value of x in this triangle. All right, let's see if you got it here. We have one missing angle in a triangle. Our triangle sum theorem is what we're applying, which is knowing that all three angles have to add up to 180 degrees. So that means x plus 40 plus 70 has to equal 180 degrees. If we combine the 40 and the 70, we will get 110, which we can then subtract from both sides of the equal sign to find the value of x here, which is just 70 degrees. We'll take a moment here to also review a little bit of classifying triangles. If this angle is 70, that makes these all acute angles, which would make this an acute triangle. In the previous example that we did, we also have an acute triangle. 27, 71, 82, all of those are less than 180. Those are both acute triangles here in this example. Okay, I'm sure you knew it was coming. We have to add algebra to this. It's not just going to be as simple as adding three values together. We're going to have expressions here and variables that we have to solve for, and some extra instructions here that we're not just solving for a variable, we're solving for the obtuse angle in this triangle. Now, we do not always want to go based off of looks. If we are, clearly this would be the obtuse angle that's in here. So we're solving for x and plugging it in there to find the measure of that angle. So first, we need the correct equation to solve for x. And again, this is applying our triangle sum theorem. So no matter how complicated this stuff is in here, I know any triangle, all three angles have to add up to 180 degrees. So I'm taking these three values and adding them up to equal 180. So we have x minus 10 plus 2x plus 5 plus 35 equals 180. And we're doing our algebra here to solve for x. I'm starting with combining like terms. I have x plus 2x, that gives me 3 x's on the left side of the equal sign. We have a minus 10, a plus 5, a plus 35. All of those combine to give me plus 30 on the left side. And to get 3x alone, we're subtracting 30 from both sides. And I get 3x equals 150. I can now divide both sides by 3 to determine that x is 50 degrees. Again, if our question only asked us to solve for x, that would be our answer. But again, we need to find the obtuse angle. This value right here. We're plugging in that 50, substituting it there for that x. So 2x plus 5 with x being 50 would be 2 times 50 plus 5. 2 times 50 is 100. 100 plus 5 gives me 105 degrees for the obtuse angle in this triangle. Let's see if you're able to add this layer of algebra in on your own with this example. As you do this, just make sure that you include that angle in your triangle sum theorem. Go ahead, pause the video, see if you can find the measure of the smallest angle in this triangle on your own. Okay, let's see how you did. Triangle sum theorem. All three angles have to add up to 180 degrees. So that is the 2x plus 1 plus the 5x plus 5 plus the right angle, 90 degrees. That have to equal 180 degrees, and we can solve for x in that equation. Like terms here, 2x and 5x give me 7x's. And we have a plus 1, a plus 5, and a plus 90, which gives us a plus 96. And we're on our way here to solving for x. I can now subtract 96 from both sides of the equal sign to get 7x equals 84. Then divide both sides by 7 to get x equals 12. Okay, from there we're plugging in to find the smallest angle. Now let's say you weren't able to identify visually which angle is the smallest, just plug it into both and then circle whichever one gives you the smallest value. For this though, hopefully you know if I'm multiplying a number by 2 and adding 1, I will get a smaller value than if I multiply the number by 5 and add 5, as long as that value is positive like ours is. All right, so I'm plugging into the 2x plus 1 to get our smaller angle here. So 2 times x, which I know is 12, plus 1. 2 times 12 is 24. 21 plus 1 gives me 25 degrees for the smallest angle in this right triangle. We have another theorem to learn here in 5.1, which is the exterior angle theorem. So we're continuing expanding our knowledge here on triangle measures. In this theorem, tells me that any exterior angle of a triangle is going to equal the sum of the non-adjacent interior angles. Remember, non-adjacent would refer to things that are not near, right? Not next to. Okay, so as we look at our example here, hopefully you can tell the exterior angle would be angle 4, and that is going to equal the sum of the angles that are not next to it in the interior of the triangle. So the interior is angles 1, 2, and 3. The one that is next to 4 is angle 3. So the two non-adjacent angles are 1 and 2. So the exterior angle theorem for this figure would tell us that the measure of angle 4 is equal to the measure of angle 1 plus the measure of angle 2. All right, so again, exterior angle theorem says an angle outside of our triangle will equal the sum of the two non-adjacent angles inside the triangle. Angle 4 equals angle 1 plus angle 2. We're going to practice applying our exterior angle theorem now to solve for missing angles or variables for triangles. In our first example here, I'm also going to give you a little review of naming angles. It's going to be important here as we're solving for angles of triangles. So our exterior angle is where this E is, this variable outside of our triangle. The name of that angle, though, we would call angle ACD. So our exterior angle, ACD, would be equal to the sum of the non-adjacent interior angles. So we would not involve this angle that's right next to ACD, which would be angle ACB. We would use these angles where the 50 and the 67 are. So this angle I can call angle BAC at the top, angle BAC. And then remember that exterior angle will equal the sum of the non-adjacent. So I'm adding that angle to this one, which would be angle ABC, where our 67 is. Measure of angle ABC. That's our exterior angle theorem. All we need to know is that this is how we're setting up problems when we get our exterior angle. Whatever that is, whatever's there, will equal the sum of those angles that are furthest away inside of our triangle. Once we understand that theorem, all we're doing is just substituting these values into the right positions for this equation. So that exterior angle ACD is where my E is. So I'm just subbing that there on the left side of the equal sign. Okay, my angle BAC is this non-adjacent angle where my 50 is, so I'm just subbing that in for angle BAC. And then angle ABC is here where my 67 is, so I'm just subbing that in for the ABC. All right, so understanding the theorem allows you to take information and plug them into your equation. So it's outside equals the two furthest away added together. Outside equals two furthest away added together. Right, then this is easy, one step here, just adding 50 plus 67, I get 117 degrees for the value of E. Right, let's see if you're able to duplicate this on your own. Knowing the setup for your equation, can you plug things in the correct places and solve for the missing angle in this example? Angle FGE, which is this angle, it's not FGE, it's only this angle, where our question mark here is. Pause the video, see if you can solve for that using the exterior angle theorem. All right, let's see if you're able to get this correct. For our next few examples, I'm gonna give you this little added visual to help. The exterior angle I'm gonna highlight in yellow. Hopefully it's obvious, it's the 98 here. Those non-adjacent interior angles, I'm just gonna circle in green. So the question mark and the 48. All right, and our exterior angle theorem says that exterior angle will equal the sum of the non-adjacent interior angles. So outside equals these added together. Again, we're just subbing these values into that theorem. So we have 98 degrees as our exterior angle equal to our missing angle plus 48. So again, as long as you know how the exterior angle theorem sets up an equation, we can just substitute things in and then solve that equation from there. Maybe that question mark is annoying you there. Let's change it into an X so it just looks like regular algebra for you. To get that alone, all we have to do is get rid of the 48 that's on that side with it. I can do that by subtracting 48 from both sides, and I find that X is 50 degrees in this example. Okay, hopefully you've caught on to the pattern here. I'm going to continue doing that little highlight that I showed you. Exterior angle here here are the non-adjacent interior angles. And again, our theorem tells us exterior angle equals the sum of those angles that are furthest away in the triangle. So as I substitute this in, we have 117 degrees equal to the unknown angle plus the 40. And again, we just have one step here to solve for x, which is subtracting 40 from both sides. And we can determine that x is 77 degrees in this example. Again, we knew it was coming. We have to add algebra to this, right, to make it a little bit more complex. We are using our exterior angle theorem again because we have an exterior angle and we have expressions for our two non-adjacent interior angles. Exterior equals the sum of the non-adjacent interior angles. So 146 equals our 5y plus 3 plus our 4y plus 8. And we're just using our algebra skills here to solve for y. So we have like terms to combine here. 5y plus 4y gives me 9y's. 3 plus 8 gives me 11. So my next line will be 146 equals 9y plus 11. I can get 9y alone now by subtracting 11 from both sides. I'm going to run out of room here, so I'm going to move over here. That'll give me 135 equals 9y. And I can now divide both sides by 9 to find out that y equals 15. And again, maybe a little tricky thing involved in this problem here is that it's not asking me to only solve for y. I must find the measure of angle ABC. And so that requires you to know where angle ABC is. Remember, the middle letter is the vertex of that angle just down here at B. This is angle ABC, the 4y plus 8. So we're subbing our 15 into that angle and then solving. So measure of angle ABC equals 4 times y, which we know is 15, plus 8. 4 times 15 is 60. 60 plus 8 gives me 68 degrees for the measure of angle ABC. Some of you may have noticed that we could have actually solved for all of these examples without using the exterior angle theorem. Just as an example, if I zoom in on this figure here, it is possible for us to find the measure of this angle right here with a linear pair. These two are a linear pair, side by side on a straight line. They have to add up to 180 degrees. So if this is 117, this would have to be 63 degrees. Then I can just use the triangle sum theorem there to solve for this missing angle. Hopefully you understand that would be two different equations you would have to do there in order to solve. So that is a little bit more work. It's also important to know that you cannot always do that to solve for the measures of triangles. There are certain scenarios like this one that become much more complicated if you're trying to think of a linear pair in order to get to a triangle sum theorem problem in your triangles. So it's best for us to know our exterior angle theorem and how to set up that equation where our exterior angle, in this case the 11x plus 8, will equal the sum of those non-adjacent interior angles. So exterior, sorry, my software is lagging here a little bit. So our exterior angle will equal the sum of those non-adjacent interior angles. So this example, we have 11x plus 8 for our exterior equal to our 3x plus 12 plus our 68 for our non-adjacent interior angles. Then we're doing algebra to solve. I have like terms here with my plus 12 and my plus 68. Those can be combined. So I got 11x plus 8 on the left. I got 3x plus 80 on the right. My x's here are on both sides of the equal sign. I need them on one side. So I'm going to move that 3x by subtracting 3x from both sides. That'll give me 8x plus 8 equals 80. Then I can get that 8x alone by subtracting 8 from both sides. That'll give me 8x equals 72. And then I can get x alone by dividing both sides by 8, which gives me x equals 9. So x equals 9. But notice the instructions I gave here said to solve for the measure of angle EDC. Again, hopefully you've caught on how we can identify angles. 3 letters, the middle is the vertex, the middle letter is D, that's angle EDC, the 3x plus 12. So I'm plugging in my 9 into that 3x plus 12 for the measure of angle EDC. So 3 times our x of 9 plus 12. 3 times 9 is 27. 27 plus 12 will give us 39 degrees for the measure of angle EDC in this example. In our last few examples here, we're going to be looking at some complex figures involving triangles and solving for missing angles. This example has 3 missing angles involved and we're solving for all of them. I'm going to go ahead and put variables here. So I'm going to put x here, a y here, a z here. And these can all be solved using either angle pairs that we've learned about in geometry or these theorems that we've just discussed here, the triangle sum theorem or the exterior angle theorem. For example, the x in this left triangle I can get with the triangle sum theorem because I have 25 and 35, only one missing angle, and I know all 3 have to add up to 180. So I can do x plus 25 plus 35 equals 180. And if I do the appropriate algebra here, I will get 120 degrees for x. From there, I can use the exterior angle theorem. Hopefully you can recognize here with what I've highlighted that x is the exterior angle to these non-adjacent interior angles, the z and the 60. So I can solve for z using my exterior, now that I know that my x is 120, equals the sum of those non-adjacent interior angles, would equal z plus 60. And again, quick algebra there would tell us that z is 60 degrees. And now I can lastly go to that triangle and do triangle sum theorem there to solve for y. Since I know z is 60, I have y and 2 60s in that triangle. They all have to add up to 180. I would also get 60 degrees for y in this example. One other route you could take in this is to use the linear pair right here with x and y. Right? If we know that this angle is 120, I know linear pairs have to add up to 180. I could get the 60 for the y there, and then I could have solved for z with the triangle sum theorem on that side. In this example, we have a lot of linear pairs that are going to help us to solve for the 4 missing angles involved. For example, 1 and 92 here, those are a linear pair. So the measure of angle 1 plus 92 degrees will have to equal 180 degrees. That would make angle 1 equal 88 degrees. All right, I'm going to go ahead and just add that into my figure here in red, 88 degrees. We have another linear pair right here. Angle 2 and 123 degrees are a linear pair. They have to add up to 180, and appropriate algebra here would give me 57 degrees for angle 2, right? 57 degrees. I'm going to do a quick exterior angle theorem here just because we've been learning it. If we're looking at this, 4 is the exterior angle. Those are the non-adjacent interior angles. So we know the measure of angle 4 will equal the sum of those angles furthest away, the 88 and the 57. If we add those together, we're going to get, let's see, 145 degrees for the measure of angle 4. And then lastly, we can look at this linear pair here with 3 and 4. Got to add up to 180. So the measure of angle 3 plus the 145 has to equal 180 degrees. And we would get angle 3 being 35 degrees in this example. Again, I didn't have to solve for 4 first. Once I had these two, I could do triangle sum theorem to get the 35 for angle 3 and then do the linear pair here to get the 145. It's really a matter of preference for an example like this. Again, we have linear pairs, exterior angles, triangle sum theorems. Got to be able to use all these to solve for variables. And that leads us to our last example here. In our last example, there's a few different things that we can do here to solve for x and y. I'm going to show you how to start using the exterior angle theorem first, and then I'll show you a different way that can be done. Our exterior angle here we can think of as y and 78 combined on the outside here of our triangle. That would make these the non-adjacent interior angles in here, and we can say that y plus 78, which would be that whole exterior angle there, would equal the sum of the 70 and the 74 there on the non-adjacent angles inside. If I move that 78 to the other side, we would get, let's see, we got 144 minus 74, so that would be 66 degrees for y. And then we can use a triangle sum theorem in this right triangle to solve for x, knowing that x plus the 90 for the right angle plus the 66 that we found there for y will have to equal 180 degrees. And in doing so there, we would be able to find that x is 24 degrees in this example. Another way we could approach this is by finding that third angle in the triangle first. So triangle sum theorem here, I already have 144 degrees here. That would make this 36 degrees. Then I can use these three angles, knowing that they're on a straight angle, they have to add up to 180 degrees. And so that would be y plus 36 plus 78 equals 180. And I would still get the same result of y being 66. And then I can solve for x with the triangle sum theorem from there, still getting 24 degrees for x. Guys, that wraps up our lesson for today. You'll see you in the next one. Bye, guys.